In this video, I'm going to go through OCR AS-level Chemistry. This is the paper 1. This is paper 2, and this is the June 2016 paper. I'll do the first half of this paper in this video and the second half in another one. Okay, so group 2 elements are metals that react with oxygen and water. Magnesium is oxidized when it burns in oxygen to form an ionic compound. Write the electronic configuration of a magnesium atom. Okay, so we've got 1s2 is filled up. We've got 2s is completely filled, so that's 2s2. The 2p subshell is filled, so 1, 2, 3, 4, 5, 6 there. And then we have 2 electrons in the 3s orbital, so 3s2. Explain what happens when magnesium is oxidized in terms of electron transfer. Well, it's only one mark. I think what you've got to say it's going to lose 2 electrons. Just to be on the safe side, you might want to say 2 electrons from the 3s subshell. Oxidation is loss of electrons, of course. Okay, so here we've got the ionization and a question about ionization energies. Okay, the first and second ionization energies of group 2 can be linked to increase in chemical reactivity down the group. The first and the second ionizations of calcium and strontium are given below. Okay, so here we've got calcium, 590, the first one, and strontium's is lower. Of course, we'll talk about that in a minute, but the reason why it's lower is because strontium is here. The electrons are going to be coming not from 4s, as is the case with calcium. The electrons are going to be lost from 5s, so they're further from the nucleus and there's more shielding and stuff. Okay. Anyway, let's write the equation for the second ionization of strontium. So we're going to have Sr. It's already lost 1 electron in a gaseous form. It's going to form Sr2 plus. That will be gaseous as well, and we've lost an electron. Okay. Explain why the first ionization energy of strontium is less than the first ionization of calcium. Sort of said that before, didn't I? Well, in the case of strontium, it is a good idea to name the subshell the electrons are being lost from, if you can. In strontium, electrons are lost from 5s. Calcium, they're being lost from 4s. Well, 5s is further from the nucleus. And you've also got more shielding. And I probably want to say, so the attractive force on the electron, which is lost, is lower. Okay, that will get you 3 marks. Okay, how group 2 metals react with water. So we've got this group 2 metal react with cold water, so of course it can't be magnesium, it must be calcium, strontium, or barium, because magnesium doesn't react with cold water. 0.162 grams of the metal produces 97 centimeters of gas measured at room temperature and pressure. First of all, draw a labeled diagram of the apparatus can be used to carry out this experiment. Right, so all you need to have is you've got your conical flask or something else like that with your water and your metal. You'll need to connect that to a gas syringe, so make sure you draw your bung like that. And there's your gas syringe. Label diagram, so you just label flask, bung, gas syringe, and this is a delivery tube. Okay. Right. It's important, if you look in the mark scheme, if you draw your bung like that, okay, with a tube coming out like this, then you'll lose a mark. They don't like that. You've got to show, the cross section of the bung with with the hole for the delivery tube. Okay, identify the metal M from this reaction and show your working. Okay, so what we're going to say is, so we're told here that 0.162 grams of the metal gives 97 centimeters cubed of hydrogen gas. And if you look at the equation there, you can see that 1 mole of metal gives 1 mole of H2. Right, so let's work out the moles of H2 from the volume then. So we're going to say moles H2 is equal to the volume over the volume of 1 mole, which is 24,000 centimeters cubed. Okay, so the volume they tell us was 97 over 24,000. That is equal to 0.004 exactly. Okay, 0.004 moles of H2. So we can say from that, therefore, we know that with the moles of metal M is going to be the same. So moles M in 0.162 grams is equal to 0.004. Now we know that moles is equal to mass over, for an element, the AR rather than the MR. So rearrange that, we get the AR is equal to moles over the mass. Sorry, mass over, so I got my right there, moles equal to mass over AR. Rearrange that, we get AR is equal to mass over moles. The mass is 0.162 grams, the moles 0.004. That means the AR works out to be 40. Okay, now which of the group 2 metals has a relative atomic mass of 40? Look in your periodic table, and it's calcium. So the identity of metal M is calcium. Okay. The student plans to repeat the experiment using the same mass of a group 2 metal from further down the group. Predict whether the volume of hydrogen produced will be greater, less than, or the same. Okay, and explain your answer. Well, let's see. We've got 1 mole of M reacts with water to give 1 mole of hydrogen. And don't forget that the moles of M is equal to the mass over the AR. Okay, so we can see here, as AR gets bigger and the mass stays the same, the moles is going to get smaller. So we've got fewer moles of M, so that means we get fewer moles of hydrogen. So the volume of hydrogen is lower. Okay. Okay, so we've got the melting points of the elements in period 3. Okay, now phosphorus and chlorine have similar molecular structures. More information about phosphorus and chlorine is given in the table below. Well, phosphorus goes around as P4 molecules and chlorine just goes around as Cl2 molecules. Okay, so the chlorine are a lot smaller. Okay, so explain the difference in the melting points of phosphorus and chlorine for 3 marks. Okay, so what we're going to say is, right, chlorine has got a lower melting point because the intermolecular forces are weaker. Now we need to say what kind of intermolecular forces do we have in each? Well, obviously in Cl2 and in P4, there's no difference in electronegativity between the atoms, they're the same. So there's going to be no permanent dipole-dipole. So the only kind of forces we're going to get are London forces. And the London forces are going to be bigger in P4 because it's a bigger molecule. It's got more electrons. So therefore it's got more points of contact, so you get stronger London forces. Okay, bigger molecules, more points of contact, stronger London forces. Okay. Right, magnesium and silicon have different types of giant structures. Okay, this is a 4 marker. Describe the bonding in magnesium and silicon. Include the names of the particles and describe the forces between the particles in the structures. Right, let's start off with magnesium first. I presume it's going to be 2 marks each. So Mg, it is it's a metallic lattice. Now, what are the particles and what are the forces between them? So in a metallic lattice, you're going to have Mg2 plus ions. I'll try and draw them in a roughly the same. So you've got Mg2 plus ions in a regular lattice, I'd say that. And they're surrounded by a sea of delocalized electrons. So what are the forces between them? Well, you've got electrostatic forces of attraction between the negative electrons and the positive ions. Right, let's move on to silicon now then. So silicon, Si, what kind of bonding have you got in silicon? Well, silicon is a giant covalent structure, very similar to diamond. Each silicon is covalently bonded to 4 other silicons, and those to 4 others, and so on. Okay, so what are the forces between the particles? Well, the forces between the particles are covalent bonds. And I think that is going to be enough for, you don't have to say what is the forces of attraction in a covalent bond, which is of course attraction of the 2 positive nuclei for the shared pair of electrons which are negatively charged. But I think just saying it's a covalent bond is going to be enough there. And say it's a giant covalent structure. Okay, actually, looking at the wording of that question, okay, there's forces and the forces and the particles. So let's say, what are the particles? They're silicon atoms. And what are the forces of attraction? The attraction for the positive nuclei to the shared electrons in the covalent bond. Just to be on the safe side, okay. Right, aluminium forms a sulfide, Al2S3, which reacts with water to form aluminium hydroxide and hydrogen sulfide. Write an equation for that. Okay, so we've got Al2S3. Now we should know aluminium always forms compounds with 3 plus ions. So aluminium hydroxide is going to be AlOH 3 times. We also get some hydrogen sulfide, tells us. Put water in there. Right, so let's have a look at that one. We are going to have to form 2 aluminium hydroxides, and we are also going to have to form 3 H2S's. So how many oxygens have we got there? Well, on the right-hand side of the equation, we have got 2 lots of 3, so that's 6 oxygens. So I think we're going to need 6 H2Os. Let's just check the hydrogens. Well, we've got 12 hydrogens here. And on this side, we have got 2 lots of 3, there's 6 there, and there's 3 lots of 2 there, 6 there, so that's balanced. So 6 molecules of water to balance it. Okay, compound A is an alkene, 1 mark. The carbon-carbon bond has restricted rotation because it's got a sigma bond and a pi bond. One difference between the pi bond and the sigma bond, well, if we just look at this, the sigma bond is like that between the 2 atoms, isn't it? Whereas the pi bond is like this. So I think what I like to say is in the sigma bond, the shared electron density, if you like, or the shared electrons lie between the atoms. And whereas a pi bond, the shared electrons are above and below but they're not between the two nuclei, are they? Not between the two atoms. That's what my preferred answer there would be. Maybe you could also say, well, the sigma bond, it consists of only one lobe, whereas the pi orbital, bonding orbital, consists of two different lobes. Right. Explain why compound A does not have EZ isomers. Okay. Well, the reason why is because this carbon atom here has got two identical groups. In this case, the methyl group attached. So it doesn't matter if you swap them around. It's not going to make any difference. It's going to be the same. Okay. Right. Now you've got to draw a structural isomer of A, which does have EZ, does show EZ isomerism. So let's do that. Right. So what I would suggest that we're going to do there is the reason why this one doesn't is because we've got these two pi groups. Okay. So two methyl groups around the pi bond. So let's get rid of that one and turn this one into an ethyl group. Okay. So that's going to become an H. That's going to become a CH2CH3. Okay, so what would you call that? I'll just draw it properly there. Draw the Z isomer. Okay, now we've got to be careful there. Now the Z isomer, we should have the two highest priority groups together on the same side. Now let's see what I've drawn there. Right, the highest priority group attached to this green carbon here is the methyl, because that's the heaviest one. The highest priority group attached to the blue carbon, which I've drawn there, is the ethyl, because that's got the biggest mass. So the one I've drawn there isn't the E form, isn't the Z form. That's actually the E form. So let's draw the Z form down here. So we've got our double bond there. Let's draw our ethyl group, the high priority group up there, the methyl group up there, and we've got hydrogens there. Right, what would you call that compound? Well, should number it that way. 1, 2, 3, 4, 5. So it's going to be pent-2-ene. Of course, it's the Z form. We should number it that way around, because if we numbered it that way around, 1, 2, 3, 4, 5, then you'd have to call it pent-3-ene, which is a bigger number. You should always use the smallest, number it so you get the smallest numbers possible. Okay, compound A, which I've drawn again before, can be made from an alcohol B by heating with an acid catalyst. Draw two possible structures for alcohol B. Right, now, when you dehydrate an alcohol, what you do is you remove an OH from one carbon and an H from the carbon next door. Okay, that's what you do, and you get rid of those, and then you turn that into a double bond there. Okay. Okay, so let's bear that in mind. Right, so I'm going to stick an OH on the right-hand side carbon for the first one. Okay, let's call it the blue carbon. So if I stick the OH on there, I'm going to get CH3, CH3, and here's the OH which I've stuck onto it, and here's the H. Okay, so when you dehydrate that, you're going to remove water, hydrogen there, and the OH there. So that's one possibility, that one there. Let's see if we put the OH onto this green carbon instead. What we're going to get instead? Well, we're going to get CH3, H, put an OH on there, and an H on there. Okay, they're the two structures for possible structures for B. Right, compound A reacts with hydrogen bromide to form a mixture of two different organic products. Okay, give the structures of the two possible products. and then outline the mechanism. Okay, so let's just draw the two possible structures. So what we could do here is we could stick, we're going to react with HBr, so we could stick an H onto that one and a Br onto that carbon, or the other thing we could have is, if you could have, if I just draw the reverse of that, so you could have, stick the Br onto that carbon this time and the H to that one, and then you'd have this. Okay, and then you've got to explain which one is the most likely. Okay, so let's do that then. So I'll draw the, so what the structure is, we have got this. Okay, and on that carbon we've got one methyl and an H. Okay, so I'll draw it like that. Now we've got a hydrogen bromide molecule comes along. Now what kind of a mechanism is it? It's going to be electrophilic addition. So here's our HBr. We've got a partial positive charge on the carbon, on the hydrogen there, and a partial positive negative charge on the bromine, because bromine is more electronegative. The first step in the mechanism is for a pair of electrons, is the pi bond moves on to the hydrogen there and forms a bond with it. And then this bond between the hydrogen and the bromine has got to break, so the pair of electrons go into the bromine. Now, of course, two things can happen there. It can either, the hydrogen can form a bond with the blue carbon, or it can form a bond with the green carbon. So let's draw both of those possibilities. Right, so we're going to get, let's say it's the hydrogen bonds to the blue one. We're going to get that. Now this carbon is going to have a positive charge on it. It's a carbocation. And we need to think, what kind of a carbocation is that? Well, this is a tertiary carbocation, because the carbon to which has got the positive charge on is bonded to three others, 1, 2, and 3. Let's see what happens if the hydrogen sticks to the other carbon instead, the green one. Right, we're going to get this instead. Okay, we're going to get, and then we're going to have the hydrogen sticking there. And this time we've got a positive charge on that carbon. Now, that's a carbocation. What kind of a carbocation is that? Well, we can see the carbon with the positive charge is attached to two other carbons, 1, 2. So this is only a secondary carbocation, which is less stable than a tertiary. So you're going to get, this is less stable than the tertiary. So you're going to get less, this will happen less. So you're going to get less of this intermediate here than of the tertiary carbocation above. Now the final step in the mechanism is for bromine, the bromide ion, which we've got from here, we form Br minus. That is going to react with the carbocation. So we've got to draw a lone pair. There's obviously 4 lone pairs on that. One of them is going to attack there. And the same will happen with this one. We know this is going to not happen as much because the secondary carbocation is not as stable. And so let's draw the main product, the major product, the one you get more of is going to be like this. And we get the bromine there on that carbon. So this is the main product. So your 6 marks then for all of the, probably 4 for the mechanism, the curly arrows and the partial charges and the intermediates. The other 2 marks will be for saying that this one proceeds via a tertiary carbocation, which is more stable than the secondary carbocation. And so this one is more likely to form as an intermediate. So you get more of this as the product than of the bromine. You know, obviously, you just see the product for that one is the bromine is going to be stuck onto that carbon instead. I just finish it off for the sake of completion. That would be the minor product. Okay, so nitrogen forms several different oxides. N2O, N2O. It's an anesthetic, and NO is involved in depletion of the ozone layer. Right. Explain in terms of bond breaking and bond making why the enthalpy change of formation of NO is endothermic. Right, I think it's a good idea. It's only 1 mark. It's a good idea to write the equation for the formation there. So we're going to have half N2 plus a half O2 goes to NO. That would be the delta HF reaction. Right. In terms of bond making and bond breaking, so what we need to do, we need to break nitrogen triple bonds and oxygen double bonds, but we form a nitrogen oxygen bond. Okay, now all we need to say is the bonds formed are weaker than the bonds broken. So you're going to get more, you're going to get you're going to have to put more energy in to break these 2 bonds than you get out from making this new bond there. Right. Right now, draw a labeled enthalpy profile to represent the enthalpy change of formation of N2O. Okay, so draw the reactants and products, but do not show the activation energy. Okay, don't show that. Right, so what we want here is we want energy on this axis, 2 marks for this, and we want a progress of reaction along the bottom one. Now this change is endothermic. Okay, so that means the products are going to have more energy. Sorry, the products are going to have, that's not the products, the reactants are going to have less chemical energy than the products have. And of course, this amount of energy here is the enthalpy change. That there, that is delta H formation, which is positive. It's an endothermic change. Now we have to write down for N2O, so we're going to have the elements of the standard states are, well, here's 1 mole of N2O there, gas. We're going to have 1 mole of N2 gas, and the standard state of oxygen is O2, so we're going to have a half O2 gas. So that is the diagram you've got to draw. Okay, so we've drawn the formulae, we've drawn the state symbols, reactants and products, and we've drawn the enthalpy change. We label the enthalpy change. I should point out it's quite important there to write the equation down as I've done it there, not to double it as 2N2 plus O2 goes to 2N2O, because of course that's not delta HF, because you're not forming 1 mole of N2O there, you're forming 2 moles, so that would be 2 times the enthalpy of formation. Right, ideal gas equation then here now. N2O is supplied in cylinders. Calculate the gas pressure in pascals. Okay, so what is the equation we need? Obviously is PV is equal to nRT, sorry, PV is equal to nRT. Let's rearrange that so we get P is equal to nRT over V. But we have to be really careful with units. The units here will be, pressure will be in pascals, not kilopascals. The volume, that is measured in meters cubed. Okay, and the temperature has got to be in Kelvin. Okay, so we have to do a bit of converting here. So the temperature is going to be 20 degrees C, so it's 273 plus 20, that's 293 Kelvin. dm cubed. Now, how many dm cubed in a meter cubed? Well, 1 meter cubed is equal to 1000 dm cubed. That's a tricky conversion. Okay, so how many meters cubed have we got? The volume is equal to 2.32 times 10 to the minus 3. Let's put all those numbers into the equation. So P, the pressure in pascals, is going to be equal to, now we need to work out N, of course. Well, we've got 187 grams. of gas. So how we're going to work out N is the number of moles. So N, which is the moles, is going to be equal to the mass over the MR. We've got 187 grams. The MR of this is going to be 2 times 14, 28 plus 16, which is 44. Same as carbon dioxide, strangely. Okay, so we've got 187 over 44. So the number of moles we've got there is 4.25 exactly. So now we are in a position to put all the numbers in there. So pressure, okay, number of moles, 4.25. R, the gas constant from your data sheet, is 8.31 joules per mole per Kelvin. Temperature is 293 Kelvin. And the volume is 2.32 times 10 to the minus 3 meters cubed. That is equal to 4.46, and that's 3 significant figures, times 10 to the 6 pascals. Yeah, it gives it in standard form, and I've given it the 3 significant figures, so that's our answer there. Okay, so NO catalyzed the breakdown of ozone in the stratosphere. Write 2 equations to show how this happens. Okay, so we get NO, which is actually a free radical. It's got an unpaired electron in it. Plus ozone, which is O3. That is going to react to give us an oxygen molecule plus NO2, which is also a free radical. So that is actually a propagation step, you'd call that, in free radical mechanisms. And the second step is for the free radical NO2 to react with an oxygen atom to form NO free radical and O2. Okay. Right, and that's as far as I'm going to go with this video. It's about halfway through the paper, and the next half I'll cover in a later video.